In this video I'm going to talk about what is called a Riemann sum. So what we are going to look at is, we've got a couple of videos leading up to this that we've started to look at these rectangles underneath a curve to estimate an area. So what we're doing is using either left or right endpoints or possibly midpoints. We're splitting an interval up underneath a curve into n number of rectangles, and then we are finding the sum of all the areas of those rectangles. Okay, and those rectangles, the height of those rectangles is determined by whether we are doing left endpoints or right endpoints or midpoints. So what this is saying is, what this sum shows is it's saying we're going to go from our first to our n rectangles, however many that happens to be, and we are taking the function evaluated at x of I. So what this means is this is the representation of the height of each rectangle, and then times delta x. Delta x is our change in x, so that it would be the width of each rectangle. So if we take the height of each rectangle times the width of each rectangle, that's going to give us the area of each one, and then we're going to add up all of those areas of those rectangles, and that's going to give us an approximation of the area underneath the curve. A quick side note here is that we are considering the area, the rectangles that are above the x-axis but under the curve, we are considering those to be positive areas. So that in this case would be all of the areas of those rectangles and all of the areas of these rectangles. We would consider all of that to be positive area. And then anything that happens underneath the x-axis, so underneath the x-axis but above the curve, we're going to consider those to be negative areas. Okay, so the two that I'm going to do here in blue, that would be a negative area, and this would be a negative area. So above the x-axis, positive area; below the x-axis, negative area. We can actually evaluate Riemann sums without graphing the curve and without actually kind of visualizing what's going on, by simply thinking about how this formula would look given the number of rectangles that we have and our interval. So we're going to look at the function f of x equals x squared minus 2x. We're going to go from 0 to 3. So what I'm doing is estimating the area under this curve and the between this curve and the x-axis over this interval from 0 to 3. And I want to do, it says with n equals 6. So what that means is I want to find this with 6 rectangles. Okay, so I'm going to use 6 rectangles, and we're going to use the sample points to find our heights. We're going to use those to be the right endpoints of this interval, of each one. Okay, so the right endpoints. And then it says, then find the Riemann sum with the sample points being the left endpoints. So we're going to do this with right endpoints and with left endpoints. So if I were to use the right endpoints, what I'm going to do is call this the area is going to equal, I'm going to use 6 endpoints, 6 intervals using my right endpoints. So I'm going to say r base 6 here. Now before I do this, I'm going to backtrack just a smidge here. We need to figure out the width of each rectangle. So the way we do that, delta x is, we're going to take our interval and subtract, so 3 minus 0, and we're dividing that into 6 equal rectangles, which means the delta x is going to be 1/2. And then what I'm going to do, I'm going to move this down a little bit so I have some more room. What I'm going to do is, again, use my right endpoints. I'm using 6 rectangles, and what I'm going to do is factor out my width. So every single one of these rectangles is going to have a width of 1/2, and then their heights are going to be determined by the function evaluated at my right endpoints. But I don't need to do 1/2 times the first height plus 1/2 times, I don't need to keep writing that 1/2. I'm going to factor out that 1/2, and then what I'm going to do is just find the height of each one of these and add those together, and if I add all the heights together and then multiply by my 1/2, that's like doing each individual area of each rectangle. So I'm going to do 1/2, and I'm going to do right endpoints. So if I know that the width of each interval is 1/2, and I'm starting at 0, my first right endpoint would be at 1/2, because my first interval would go from 0 to 1/2. So the way I'm going to represent this is I'm going to say f of 1/2. And then I'm going to add to that, the next interval would go from 1/2 to 1, so my right endpoint of that interval would be 1. And then since my delta x is 1/2, I know that I'm just going to keep adding 1/2 to get my next height. So then f of 2.5, and then my last one would go from 2.5 to 3, so my right endpoint would be 3. Something you should check is make sure that you have 6 rectangles represented here. So I have 6 heights. If I count those out, each one of those heights is going to be multiplied by this 1/2. And then what I would do is using we could use Desmos to help us with this. If you type in your function, so our function is x squared minus 2x. What I'm going to do is I'm going to say, well, we know our area is 1/2 times, and if I use right endpoints, my first one was f of 0.5. And because I called this function f, it's going to pick up the function f here when I do this. So I can just type in plus f of 1, plus f of 1.5, and so forth until I get to f of 3. And that gives me an area of 0.875. What that tells me, so this is an area of 0.875. What that tells me is there's pretty close to equal amounts of this above and below the x-axis using my right endpoints. Slightly more above the x-axis, right? It's a positive area. So I've got more area of rectangle above the x-axis than below. Okay, so I'm going to do the same exact thing with left endpoints. So my area with left endpoints, again using 6 rectangles, I'm going to do the same thing. They have a width of 1/2. The only thing I have to change is that my first rectangle, the rectangle going from 0 to 1/2 as its x, I'm determining my height using left endpoints, which means I'm going to use 0 to determine the height of that one. And then I'm going to count by 1/2, so f of 1/2, and so forth. And I'm going to end with my left endpoint of my last interval, which is 2.5. Right, the last one goes from 2.5 to 3. Again, check to make sure that you have 6 rectangles whenever you do that. So, quick thing is, basically all that we replaced here then is we replaced the f of 3 with the f of 0. All the other ones match up. So if I did this calculation, I'm just going to go here and replace 3 with 0. And that's going to give me my estimate using left endpoints, which is negative 0.625. Okay, so using right endpoints, we had more area above the x-axis. Using left endpoints, we had more area below the x-axis. Now, both of those are estimates of the actual area between the curve and the x-axis over that interval from 0 to 3. I'm going to show you visually what this looks like. Again, I found all of this without even having to think about what the graph looks like or to draw those rectangles. I don't need to really do any of that when I'm doing a Riemann sum if I know what the formula looks like. So here's an example. This is the exact graph, x squared minus 2x. We're going from 0 to 3, so it's just looking at it from here to here. As you see that with the dashed lines here. In this case, we are doing our left endpoints with 6 rectangles. So from 0 to 1/2, it's using the height at 0, which is 0. So it's showing this green line across here for this first rectangle. But again, that one really has no area to it because the height is 0 there. But then the next 3 rectangles are all below the x-axis, so that's all negative area. And then we have another one with height 0, so there's really no area here. And then the only rectangle that I have with positive area is this last one from 2.5 to 3. If I change this to right endpoints, notice how we have much more positive area this time and less negative area, which is why we ended up with a positive value for our Riemann sum here. Okay, so very similar to what we've been doing previously in some videos leading up to this. We're taking an area, we're estimating it using rectangles, but we're not actually having to visualize it with the Riemann sum because we can figure out the width and the height using our function.